Imagine a tunnel that could take you from one end of the universe to the other, instantly. A shortcut through space and time itself. The kind of cosmic bypass that seems pulled straight from the pages of science fiction. This is the idea behind a wormhole. In theory, a wormhole is a bridge, a hidden passage through the fabric of space-time, capable of connecting distant regions of the universe, or even different universes entirely. It's a mind-bending concept rooted in Einstein's theories and extended by some of the most advanced physics ever proposed. But are wormholes real? Or are they just elegant equations with no anchor in reality? In this episode, we dive into the science behind wormholes, their mathematical origins, the physics that supports and challenges them, and whether the universe might actually be hiding one somewhere out there, waiting to be found. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel in the fabric of space-time that connects two separate points in the universe. If space is like a two-dimensional sheet, then a wormhole is like folding that sheet so that two distant points touch and poking a hole through. Instead of traveling billions of light years across space, you'd move through the tunnel and emerge almost instantly on the other side. The idea first emerged in 1935 when Albert Einstein and physicist Nathan Rosen used the mathematics of general relativity to propose such a structure. According to their equations, black holes, regions of space where gravity is so intense that nothing can escape, could, under specific conditions, be connected to their opposites, white holes, theoretical objects that eject matter and cannot be entered from the outside. Connecting a black hole and a white hole mathematically formed a wormhole. But there was a catch, one that continues to haunt the concept to this day: stability. Wormholes, as described by Einstein and Rosen, are not stable. In fact, under general relativity, a traversable wormhole, one you could actually pass through, would collapse instantly due to gravitational forces, closing off the passage before anything could travel through it. To hold a wormhole open, you'd need something exotic, a substance with negative energy density and negative pressure, something that pushes space apart instead of pulling it together. This is where exotic matter comes in, a hypothetical form of matter that doesn't behave like anything we've ever encountered. It would have to counteract the intense gravity inside a wormhole and prevent it from collapsing. Theoretical studies in the 1980s and 90s, particularly by physicist Kip Thorne, showed that traversable wormholes might be possible if exotic matter exists and in the right configuration. But here's the problem. We've never observed exotic matter in the required quantities. And while quantum physics hints that small amounts of negative energy can exist, such as in the Casimir effect, using it to build or stabilize a wormhole is purely speculative, at least for now. Wormholes don't just challenge our understanding of space, they bend the rules of time, too. In theory, a wormhole could be turned into a time machine. If one mouth of the wormhole were accelerated to near light speed, or placed in a stronger gravitational field, time would pass more slowly for it due to the effects of time dilation. When the two mouths are brought back together, there would be a time difference between them. Step into one side, and you could emerge in the past or the future. This concept, while theoretically sound within the framework of relativity, raises a swarm of paradoxes. What happens if you go back in time and prevent the wormhole from being created? Would that erase your trip? Could the universe even allow it? Physicist Stephen Hawking once proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel to preserve causality. Some theorists argue that quantum effects would destroy the wormhole the moment it becomes a time machine. Whether the universe permits time travel remains an open question. But the mere possibility links wormholes to one of humanity's deepest obsessions, rewriting the arrow of time. Could wormholes actually exist in the universe? Not as ideas, but as real cosmic phenomena? Some theories suggest they might. In certain models of the early universe, primordial wormholes could have formed during the Big Bang, tiny tunnels created by quantum fluctuations in the hot, dense fabric of spacetime. Others speculate that black holes could contain wormholes at their cores. If a black hole had the right internal geometry and was lined with exotic matter, it could potentially lead to another region of space, or even to another universe. But no observations to date confirm the existence of such tunnels. Even if wormholes do exist, they would likely be incredibly unstable or hidden behind event horizons, making them nearly impossible to detect with current technology. We've observed strange gravitational phenomena, like lensing effects and fast radio bursts, but none have definitively pointed to wormholes. Still, theoretical physicists continue to refine models. Some even propose that the universe itself could be part of a vast network of wormholes, a cosmic web of hidden connections waiting to be discovered. In recent years, wormholes have become more than just a curiosity of general relativity. They've taken on new life in quantum physics and string theory. One of the most exciting ideas comes from the ER equals EPR conjecture, proposed by physicists Leonard Susskind and Juan Meldacena. It suggests that wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen pairs, might be two sides of the same coin. In other words, every pair of entangled particles could be connected by a tiny wormhole. This concept hints at a deep link between the geometry of space-time and the mechanics of quantum information, possibly pointing toward a unified theory of quantum gravity. Additionally, in 2022, researchers using simplified models in quantum computing environments were able to simulate wormhole-like behavior in lab conditions. Not actual wormholes, but mathematical analogs that behave similarly under controlled rules. While these advances don't prove wormholes exist, they suggest we're getting closer to understanding the strange fabric of the universe and how space-time itself might be more flexible, more connected than we ever imagined. Right now, wormholes remain theoretical constructs. They're supported by the math of general relativity, extended by quantum theory, and visualized in everything from chalkboard equations to Hollywood blockbusters. But no physical wormhole has ever been observed. We don't know how to create one. We don't know how to stabilize one. And we certainly don't know how to survive a journey through one, assuming the laws of physics even allow such a thing. Still, the idea persists, because wormholes represent something larger than physics. They represent possibility. The possibility that the universe is stranger than we think. That distances can collapse. That time can bend. That what we see is only a fraction of what's really out there. Wormholes sit at the edge of science and speculation, part theory, part dream. They challenge our understanding of space, time, and what it means to move through the universe. They may never become more than elegant solutions in Einstein's equations. Or perhaps they're out there, waiting in the shadow of a black hole, hidden in the early light of the cosmos, or scattered like seeds across the fabric of space-time. Whether real or theoretical, wormholes continue to inspire scientists, storytellers, and seekers of truth alike. Because in the search for wormholes, we are really searching for something else, a deeper understanding of reality, a glimpse into the unknown, and a way to connect the distant corners of space and of imagination.